Fellow history enthusiasts, let me take you inside a bombed-out factory in Warsaw, 1943. While Nazi forces controlled every legitimate weapon in the city, Polish resistance fighters were turning scrap radiators into submachine guns, transforming bicycle parts into grenades, and converting water pipes into mortars that would help level the playing field against one of history's most mechanized armies. These weren't crude, improvised weapons. They were engineered solutions born from necessity, designed by people who understood that survival meant innovation. The same scenes played out across occupied Europe, in Pacific Island caves, and behind enemy lines where regular soldiers found themselves cut off from supply lines. From the Sten gun factories hidden in British garages to the Liberator pistols airdropped to French resistance cells, World War II became history's greatest laboratory for improvised weaponry. What emerged wasn't just desperation. It was engineering genius applied under the most extreme circumstances imaginable. These weapons didn't just win battles, they changed how militaries think about logistics, manufacturing, and the relationship between industrial capacity and combat effectiveness. The techniques developed during those desperate years continue to influence military engineering, survival training, and emergency preparedness to this day. More importantly for us as students of history, they demonstrate how human ingenuity responds to existential threats when conventional resources disappear. The British Sten gun revolutionized underground manufacturing. The Sten gun represents perhaps the most successful improvised weapon program in military history, proving that effective firearms could be manufactured in bicycle shops, garage workshops, and bombed-out factories across occupied Europe. British engineers deliberately designed the Sten for production using basic metalworking tools and scrap materials, creating detailed plans that resistance groups could follow with minimal industrial infrastructure. You know, the genius of the Sten gun really lay in its simplicity rather than any sort of sophistication. The receiver, for instance, was just formed from a single piece of steel tubing. The barrel itself, that came straight from standard plumbing pipe. And the firing mechanism, well, it only needed some basic springs and a machine bolt, nothing too fancy. In fact, resistance workshops over in France managed to produce thousands of Sten guns using car parts, plumbing supplies and salvaged steel from destroyed buildings. Quite resourceful, if you ask me. Understanding the Sten's design principles, I reckon, offers some pretty practical insights for anyone interested in metalworking or mechanical engineering. The weapon worked as an open-bolt blowback system, which basically means the bolts stayed open until firing, then the recoil energy cycled the action for the next round. This clever setup did away with complex timing mechanisms and made the weapon remarkably reliable, even in the roughest manufacturing conditions. These days, modern workshop enthusiasts can apply the very same principles of mechanical simplicity to build reliable mechanisms from basic materials, whether it's for legitimate purposes like pneumatic tools or, well, mechanical devices. Polish resistance fighters, they transformed everyday objects into combat weapons. The Warsaw Ghetto Uprising is a powerful example of how ordinary household items could become effective weapons when traditional arms just weren't available. Polish fighters managed to convert kitchen knives into bayonets by welding them to steel rods. They turned glass bottles into incendiary devices using gasoline and cloth wicks, and even made single-shot firearms out of metal pipes using improvised firing pins and springs from old furniture. Resourcefulness at its finest, really. One of their most effective innovations involved converting old radiators into multi-barrel weapons. The parallel tubes provided ready-made barrel clusters, while the cast-iron construction could withstand significant pressure from improvised gunpowder charges. Resistance fighters welded firing mechanisms to the back of radiator sections, creating weapons that could fire multiple projectiles simultaneously with devastating effect at close range. The practical application of these techniques extends beyond military history into understanding how mechanical systems work under stress. The radiator conversion demonstrates principles of pressure containment, parallel systems, and improvised ignition that will actually apply to many modern engineering challenges. Anyone working with pneumatic systems, hydraulic mechanisms, or high-pressure applications can learn from how these improvised weapons managed force distribution and system reliability using only scrap materials. Pacific theatre soldiers created mortars from water infrastructure. American and Australian forces isolated on Pacific islands developed sophisticated mortar systems using abandoned Japanese water pipes, construction materials, and naval shells modified for ground combat. These improvised mortars proved so effective that, in fact, official military manuals began incorporating their design principles for emergency situations. So, the basic construction involved welding a base plate to the bottom of a large diameter pipe, then adding elevation and traverse mechanisms from salvaged machinery and, well, creating firing mechanisms from rifle parts or improvised electrical systems. The key innovation, though, was developing proper ammunition from whatever materials were available. Soldiers learned to modify naval shells, create propelling charges from available explosives, and even fabricate fuses from timing mechanisms salvaged from destroyed equipment. These improvised mortars, honestly, demonstrate fundamental principles of ballistics and mechanical engineering that are still relevant today. The elevation and traverse mechanisms show how simple lever systems can provide precise control over, quite complex mechanical systems. In modern workshops, this includes understanding how gear ratios affect precision, how mechanical advantage works in positioning systems, and how improvised materials can sometimes substitute for precision-manufactured components when they're properly engineered. Resistance groups developed explosive devices from industrial waste. European resistance movements, you see, perfected techniques for creating powerful explosive devices using materials available in bombed cities and abandoned factories. They discovered that certain industrial chemicals, when combined properly, could create explosives more powerful than traditional gunpowder, all while using materials that occupying forces didn't really monitor closely. The most successful designs, involved combining agricultural fertilizers with fuel oil metal shavings and timing mechanisms salvaged from clocks or electrical equipment. Resistance fighters, they learned to shape charges using metal containers to direct explosive force, create reliable detonation systems using basic electrical circuits and time delays, using chemical reactions or mechanical systems. Understanding these historical techniques provides insight into chemistry, metallurgy, and mechanical systems that honestly extend far beyond their original military applications. The shaped charge principles demonstrate how metal containers can focus and direct force, concepts that apply to modern industrial processes, demolition work, and even automotive applications where controlled force direction is essential. Soviet partisans converted farm equipment into mobile weapons platforms. Behind German lines, these partisan groups transformed agricultural machinery into mobile weapons platforms that could engage enemy forces and then disappear into the countryside disguised as farm equipment. They mounted salvaged tank guns on reinforced tractors, converted truck beds into multiple rocket launchers, and created mobile repair facilities that could manufacture ammunition and parts in remote locations. The most successful conversions, involved reinforcing tractor frames to handle heavy weapons recoil, creating ammunition storage systems that looked just like agricultural supplies, and developing camouflage systems that made military equipment pretty much indistinguishable from farm machinery. These weapons, they proved devastatingly effective against German supply columns and rear area installations. The engineering principles behind these conversions honestly apply directly to modern heavy equipment modification and mobile workshop design. Understanding how to calculate load distributions, reinforce existing structures, and create multi-purpose mechanical systems actually provides valuable knowledge for anyone working with heavy machinery, mobile equipment, or adaptive engineering solutions. French underground fighters perfected single-shot assassination weapons. French resistance cells developed sophisticated single-shot weapons designed specifically for close-range assassination missions in urban environments. These weapons, you see, needed to be completely silent, easily concealed, and simple enough for non-technical operatives to manufacture and maintain using basic workshop tools. The most effective designs used crossbow mechanisms with steel bolt projectiles, spring-loaded devices that fired sharpened metal projectiles, and compressed air systems that could launch deadly projectiles with minimal noise signature. The key innovations involved creating reliable trigger mechanisms from common materials, developing projectiles that were both accurate and lethal, and designing weapon systems that could be completely disassembled for concealment. These historical weapons demonstrate principles of mechanical energy storage and release that have broad applications in modern engineering. Understanding how springs store and release energy, how compressed air systems work, and how simple trigger mechanisms can control complex mechanical systems provides knowledge applicable to pneumatic tools, mechanical devices, and precision equipment design. Italian partisans created anti-vehicle weapons from railway materials. Italian resistance fighters operating in mountainous regions developed effective anti-vehicle weapons using materials salvaged from damaged railway infrastructure. They discovered that railroad rails could be converted into powerful shaped charges capable of disabling tanks and armoured vehicles, while railroad spikes and steel components provided projectiles for improvised cannons. The construction process involved cutting rail sections to specific lengths, welding steel plates to create directed charges, and developing detonation systems that could be triggered remotely or by vehicle contact. These weapons proved devastatingly effective against German convoys moving through mountain passes where traditional anti-tank weapons weren't available. The engineering principles demonstrated by these railway conversions show how structural steel can be repurposed for high-stress applications, how cutting and welding techniques can modify existing materials for new purposes, and how mechanical trigger systems can operate reliably in harsh environmental conditions. Modern applications include understanding structural modifications, heavy metalworking techniques, and reliable mechanical systems design. Norwegian saboteurs developed precision demolition tools from skiing equipment. Norwegian resistance operatives created sophisticated demolition tools using materials from their skiing and mountaineering equipment combined with explosives and metal components salvaged from destroyed military installations. These weapons needed to function reliably in extreme cold conditions while being portable enough for long-distance wilderness operations. The most successful designs incorporated ski bindings as precision timing mechanisms, used aluminum ski poles as containers for explosive charges, and converted climbing hardware into reliable detonation systems. The key innovations involved creating waterproof explosive containment systems, developing timing mechanisms that worked at sub-zero temperatures, and designing delivery systems that could be accurately positioned using skiing and climbing techniques. Understanding these cold-weather engineering solutions provides valuable knowledge for anyone working in extreme environments. The techniques for maintaining mechanical reliability in freezing conditions, creating waterproof containment systems, and designing equipment that functions reliably despite temperature extremes apply to modern outdoor equipment, automotive systems, and industrial applications in harsh environments. Here at In the beginning, we explore how desperate circumstances throughout history have driven remarkable innovations that continue to influence modern engineering, military science and survival techniques. These World War II improvised weapons represent the pinnacle of necessity-driven engineering, demonstrating how human ingenuity responds when survival depends on creating something from nothing. The techniques developed during those desperate years offer more than just historical curiosity. They provide practical knowledge about metalworking, mechanical systems, chemistry, and engineering principles that remain relevant for anyone interested in, understanding how things work and how to make them work better. If this deep dive into wartime innovation has given you a new appreciation for the engineering challenges our predecessors faced, go ahead and subscribe to our channel and ring the notification bell for more content that connects historical ingenuity to modern applications. Share this video with fellow history enthusiasts who understand that the past offers honestly the most practical education available. These weren't just weapons. They were solutions created by people who refused to accept that superior resources guaranteed victory. History shows us that knowledge, creativity and determination often matter more than industrial capacity, and those lessons remain as relevant today as they were in the factories and workshops of occupied Europe.